Okay, so we've got 360 grams of some substance. Specific heat is 1.5 joule per gram Celsius, or 1,500 joules per kilogram Celsius. Okay, that kilograms, 1,000 times a gram. So the number here has to be 1,000 times as great as this one to get the joules per kilogram Celsius. Okay, well, we're going to use this because this is given in grams, and we immerse this in water. "35 grams of ice water." This is at, what is the temperature, 46. Degrees Celsius. Equilibrium achieved at 20 degrees Celsius. The question is, how much ice was there in the ice water? Okay, well, whatever the substance is, and that would be somewhere in the neighborhood of the specific heat, and a little lower than the specific heat of concrete or stone, but more than the specific heat of most metals. Okay, so I don't know what substance that might be. A ceramic is usually pretty much the same as stone, but I'm no expert on that, so I'm sure there's something. Okay, anyhow, the substance, whatever the substance is, it loses heat. We'll call this delta Q1. And that's going to be 360 grams times 1.5 joules per gram Celsius times the temperature it comes to. Now that's the change in the heat of that substance, okay? And we take the final temperature minus the initial temperature, so that final minus initial is the change. Well, that change is negative 26 Celsius. 360 times 1.5 is 540. 540 times 20, and then times 26. This approximates that as 11,000 joules. I think it might be a little higher than that. But let's just say that's it. Okay. Then you want to think of it in terms of loss and gain. The ice water gains 11,000 joules. Okay. Melted water, call that WQM. Let's call this WQS for substance. WQM for melted water, or MW for melted water, just to make sure we understand what it means. It's approximately 4.2, it's a little less than 4.2, 4.2 joules per gram Celsius times and I say melted water. This is ice water. It's a combination of ice and water. It's the ice that melts. melted ice and the water, okay? Gains, heat. Water melts at 0 Celsius. Incidentally, ice water is at 0 Celsius because it's a mix of ice and water. So that's 700 times 4.2, which is 2,800 and 2,940. So we'll say approximately 3,000 joules is close enough for an indication. You can do the accurate numbers. And well, yeah, I gained 8,000 joules. Okay. Now, the fusion of the water, approximately 330 joules per gram. This is the heat you got to add to the crystal structure of ice, so that in a slightly oversimplified way of understanding it, the oscillations, vibrations of the molecules in the crystal structure of the ice increase until the crystal structure is destroyed and you've got the liquid water still at 0 Celsius. And it takes 330 joules for every gram of ice at 0 Celsius to do that. Now the ice is at 0 Celsius. I'm not writing down all the conditions, but you gotta kind of understand all that. Okay. So to gain 8,000 joules in melting, requires 8,000 joules for water is gaining at 330 joules per gram. Okay. So I'm saying this is maybe about 24 grams of ice. Now you can set this up as a single equation. Delta Q total is 0, so deciding whether I want to write this out in symbols. I don't have good symbols right now, so I'm going to go ahead and write out the numbers. Your 360 grams times 1.5 joules per gram Celsius times 20 Celsius minus 46 Celsius, which is the change in the heat energy of the substance. Plus let's say the mass of the ice little boxed up here. The mass of the ice times the 330 joules per gram that the ice loses times the I needed that room anyway, so I'm glad I didn't have to write that out. I don't know why I was writing that. Didn't make any sense. Thinking ahead to the next step. Okay, then. Plus 35 grams times 4.2 joules per gram Celsius times 20 Celsius minus 0 Celsius equals 0. There's your equation. Now you can write all this out in symbols and solve for the mass of the ice, because it's the only unknown. But just multiply things out and everything, it'll come out the same as this analysis. So that's kind of an intuitive analysis, but you want to think at a little higher level about energy conservation and just write it all out as one equation. But it doesn't hurt to think this through. It's more intuitive. This is more formal. Okay. You want to be able to do both. Just a little clearer view of this whole board. I didn't realize till I started trying to line this board that about this much of this board was gone. So you kind of lost the 20 Celsius minus 46 and so forth. So there it is. It's very simple actually, but you got to think it through. Okay, so enough of that. That's from earlier in the course. We got a midterm coming up. We had a question. Okay. Okay, so we've just done this with the generator, the hand crank generator, and the 1 farad capacitor. What we essentially had was a circuit like this. We had a voltage source, which in this case was the generator. We didn't have a switch, but this switch was, okay, you hook this up. Okay, so we got a switch. We could close the switch and now the capacitor start to charge. Meaning that we're going to move electrons from one terminal to the other. Now, this means the electrons are going to go from here over to here because the current goes away from the small terminal, that's positive. Okay, so it's like you're moving positive charges this way. And I just said it wrong. Just like you're moving electrons this way. Okay, so you move electrons from here to here because this is going to end up positively charged. Just set it backwards. Okay, so you have this situation. Okay, let's go ahead and put a resistance in here. So we don't have what would essentially be a short circuit between here and there, and maybe melt the wires and damage the capacitor and everything. So we'll put some kind of resistance in. Okay, so what's going to happen? Well, you throw the switch, you start building charge on the capacitor. Okay, so now the capacitor has some charge. It's got some negative charge here. And some positive charge here. Well, that induces an electric field. Across capacitor, which means multiply that field by the distance between these plates, and you get a voltage. And that voltage, well, okay, this is the positive end of the source, and this is the negative end. Okay. This is the positive end of the capacitor. This is a negative end, right? So if you're moving from here around here in the counterclockwise direction, you get a positive voltage across here. Okay, voltage here, R in the voltage here. Meaning the voltage across this resistor, well, it's like this one is pushing electrons this way, and this one is pushing electrons this way. Or if you want, this is pushing positive charge this way, and this is pushing positive charge this way. Either way you look at it, this capacitor is opposing the voltage of the source. Meaning that there's less EMF across the capacitor. And so this creates all this resistance R. The EMF across the resistance R decreases. So the current, which is your EMF divided by R, well, between here and here, your voltage V sub R, the voltage across the resistor, is voltage of the source minus voltage of the capacitor so your current is voltage of the source minus voltage of the capacitor divided by R. Well, your current is how much charge is passing any point in the circuit. Well, whatever charge goes through this resistor gets deposited on the capacitor. I don't have room to write that out, so I'm gonna flip this board and give myself room. Well, your average current is equal to the average rate of change of the charge with respect to time, right? But your current then is instantaneous current is just the derivative, dq dt. Okay. The rate at which charge is passing any point in the circuit. Okay. Now, any charge that passes any point in the circuit ends up being deposited on the capacitor. Okay. You got this drift of charge. Whatever charge drifts to this point stays there. And an equal charge will drift away from this point. Okay. Building up positive charge here, negative charge here. Increasing the electric field, thereby increasing the voltage of the capacitor and the voltage that opposes the voltage of the source, which decreases the voltage of the source minus the voltage of the capacitor. So dq dt is voltage source minus voltage capacitor over R at any instant. Now, voltage across the capacitor equals the capacitance times the charge on the capacitor. Now that goes back to the definition of capacitance, which I have to assume, but it's, capacitance is just the charge per unit, the voltage per unit of charge. So you multiply the voltage per unit of charge, which is a capacitance, times the charge, you get the voltage. So dq dt is voltage source over R minus CQ over R. Or well, you're taking differential equations right now. You should instantly recognize this is a separable equation. So I can dispose of this very quickly. Just get to integrate these. What you have on this side is going to be minus 1 over C times the natural log of the absolute value of V is source. Minus C cubed. And this is going to be C over R. So that the natural log of this is negative C over R times T. Meaning I should be getting an RC in this thing. Can't be doing anything wrong in this I've got. Let's see. Okay, let me back up a second. Okay, I've done something really bonehead here. If capacitance is charged per unit voltage. So a big capacitor holds a lot of charge for little voltage, just like the one we saw. And that means what I wrote here is wrong. Put it across the capacitors, Q over C. And I should have recognized right here, because I know I'm going to get an RC. And that's going to complicate the equation a little bit, so I'm going to apologize. So I'm going to just kind of wipe out everything I did here. So I'm going to write it this way. Now, if I separate it, and I want to write an R there. Okay. Now, I hope this is going to work out. I'll do this morning. Looking ahead. This leads to natural log, the absolute value C V source minus Q equals negative DT over RC, which leads to Now, don't want to get into that. I'm just going to say, okay, this is equal to negative dt over RC, provided the charge is less than C times V source. Now, C times V source is the charge you would have on your capacitor if its voltage was equal to the source voltage. So assuming CV source is greater than Q. And in this case, we're talking about charging up the capacitor. So we have this. Okay, so and of course, we're exponentiating both sides. You get e to the minus t over RC. So the Q write this. Left off my integration constant, which you gotta have. There's no D in here. T over RC. Okay. Now it's right. Now e to the K is again, okay. We have the for CV source greater than Q. The reason I got to specify this is if CV source is less than Q, then the quantity you have under here is negative. So the natural log of the absolute value will be the negative of this. So this will equal the negative of this, and it's going to change the equation. Okay. Right now, I'm going to say let A equal e to the K. And A is greater than 0. Whatever your value of K is, whether positive or negative, e to the K is positive. Okay, so e to the K has to be greater than 0. So we observe that if A equals e to the K, A can be greater than 0. And A can be any number at all, depending on the configuration per system. And yes, maybe all of that board. Okay. Then you get this. We're charging the capacitor. The charging is going to end when the voltage across the capacitor is equal to the voltage of the source. So that's going to happen when the charge of the capacitor is C times the voltage of the source, okay? Because charge of the capacitor is capacitance times the voltage. So we're going to call that QF. QF again being the charge when the charging stops. Okay, when the voltage across the capacitor is equal to the voltage across the resistor. So QF such that QF, CQF equals the voltage of the source. That's when the charging ends. That's QF minus A e to the negative T over RC. If Q equals 0 and T equals 0, then we can evaluate the constant A. Q is 0. Well, e to the 0 is 1. So A is QF. Thus, of course, that's voltage of the source times the capacitance. Usually we write capacitance first. Okay, QF is capacitance times voltage of the source. So you have capacitance times voltage of the source times 1 minus e to the negative T over RC. Well, graph 1 minus T over RC, e to the negative T over RC. E to the negative T over RC is going to have a curve that looks like this. So the negative, and this is 1. Negative T over RC is this. 1 minus e to the negative T over RC. You move this up 1 unit. So you move up 1 unit here. You move up 1 unit here. You move up 1 unit here. Move up 1 unit here. That's kind of a small unit, but okay, a little higher. And you get I didn't do that very well, but you get a curve that approaches 1. Okay. This is y equals 1. Doing pretty well with this picture until I got to this point. So yeah, every point on this curve is 1 unit higher than this curve. It's badly drawn now, but there's your 1 minus e to the negative t over RC. And how quickly this thing approaches 0 depends on the reciprocal of RC. Okay, if this is where y equals c times v source, then your curve is going to look like this. It's going to be an exponential approach. That horizontal line. So now if this is Q and this is time, then this is just a graph of what we've got here. Which is just C V source times 1 minus e to the negative t over RC. If you multiply every y value in this curve by CV source, this is what you get. It looks just like this. And the speed with which it scales, the half-life, is when e to the negative t over RC equals 1/2. Not actually half-life in this context, but same idea. Dash log of half is about 0.7. T is 0.7 RC. So half-life, we mean we go halfway from here to here. Okay. And right here, T is approximately 0.7 RC. So the RC product tells you how quickly the voltage is going to approach this. In the case we just did, how long did it take before the thing felt about half as hard to crank as it did originally? 10 seconds? Maybe, something in the ballpark, more than a second, less than a minute. 10 seconds seems reasonable. So in that case, your curve would look like this, where this would be 10 seconds. Well, you can see what we did in lab. It was the day you missed. Okay, if we go back to this picture, again, we see that the rate at which charge flows here is proportional to the difference between source voltage and the capacitor voltage. So the rate of change of the capacitor voltage is proportional to the voltage of the source minus the voltage of the capacitor. That led us to the differential equation, which I screwed up there for a minute because I did something stupid. Okay, got my C in the numerator rather than the denominator because I didn't stop to think. But the further you are, the further the capacitor voltage is from the voltage of the source, the faster it's going to change. Closer the voltage of the capacitor gets to the voltage of the source, the more slowly it's going to change. And that seems to be exactly what this curve is telling us, right? And the differential equation, very straightforward differential equation, standard stuff that you were tested over a month ago. Okay. And whether you look at it the same way I did or not, you know, I think you recognize all the steps. And you should be aware from first semester calculus on that when something changes at a rate that's proportional to itself, you get an exponential. Okay, that's a compound interest. Okay, radioactive decay. You see all those things in first semester calculus, I hope. So just another instance of that. If you were discharging the capacitor, say you didn't have a source there, you would start with charge Q in the capacitor. The voltage would be Q over C. Okay. And your differential equation would be real quickly. No source, close the switch. So your current equals Q over RC, whatever Q is. We'll call that, try it this way, I T equals Q T over RC. And dQ dt equals negative I, which is negative Q over RC. So dQ dt is negative Q over RC. Well, you get absolute value of Q is e to the negative T over RC plus constant, which works out like this, but much simpler. So we could have started with that, but since you are not taking differential equations, I chose to start with the source because that's what we did with the generator. If you charge this thing up, take the leads off of the capacitor or open a switch, then the capacitor will remain charged until you discharge it through some resistance. So we can now take that capacitor, hook it up to resistance, take the interface, and watch the curve. Okay. You would get Q equals Q naught e to the negative T over RC. Now let's done rally. As we there, there it is. So the mathematics is really simple. If you get the definition of capacitance right, which I screwed up at the beginning, okay? And there you have it. Now, this leads ultimately to what happens in an alternating circuit. Just think about this. If you're cranking this thing forward, we did this in lab, cranking this thing forward, the current goes up like this. Now you crank it backward. Well, now the voltage of the source is down here. It's going to exponentially approach this. But then you reverse it again, it starts going up again. So it goes up, comes down, goes up, comes down, always exponentially approaching whatever the voltage of the source is. That's what happens if you put a capacitor on an AC circuit or an AC voltage, 60 hertz AC. If your time constant is long, then the thing never has time to pick up any voltage. Okay, it just goes up a little bit and then it decreases down toward this, but doesn't get very far before it reverses again. Okay. And what that does is it filters out your current. And that's kind of the basis of an idea of a high frequency filter. We'll get into that, but that's in a later chapter, but that's kind of one of the advantages of capacitor. We also have inductors, but we can't talk about inductors until we talk about magnetism. That's coming up next week. Just something to look forward to live forward, to know, to live for, to look forward to. Okay.